name is Jasmine Huang. This is software development and testing. We are class 16. We are going to talk about fractals, and Juan's group will come up and talk about where fractals come from.
Hello everyone. So today's presentation, we're going to start by talking about the classification of fractals. Gundo, can you tell us what fractals are?
Sure, Juan. Thank you, man. So we're going to start off with what is a fractal. Now, simply put, a fractal is a never-ending pattern, but that encompasses a lot of things. What do I mean exactly by a never-ending pattern? Well, let's go with. So a never-ending pattern, well, what do I mean by a never-ending pattern? So fractals are infinite patterns that are similar across different scales. They are repeated processes that loop over and over again. And we'll delve deeper into this further into our presentation. But so if you play it for now, okay, yeah. So one of the basic examples of a fractal in our world right now would be a fern. Stop it. Stop right there. Okay, one of the basic examples of fractal in nature itself is a fern. So as you can see, the basic layout of a fern is the main stem that comes up the middle. Okay. Well, let's go ahead. The basic stem that comes out the middle, and then the branches that come off the sides, which would be the basic layout of a fern. And the next slide. There you go. And then, if you zoom in further, you can see that the branches that come off the side also have the same basic layout as the main fern itself, which would be the main branch that comes down the middle, and the leaves that come off the side. But if you look even further on each individual leaf itself, you can see that the fern has still the same basic layout, where there's a branch that comes down the middle, and then each individual leaf itself comes down from the same pattern as the main fern itself. And then if you zoom in any further, it kind of distorts and blurs the picture. So just look at it from here. You can kind of see it that each leaf individually has the same pattern, where it has a main stem that comes down the middle, and then each individual line that comes off the side that gives off a fern kind of image. So now we've talked about what a fractal is and the basic layout of a fractal, or an example that I showed was fern. Now if we talk about a more famous fractal, which would be the Mandelbrot set, which is this image right here. Now this Mandelbrot set was named after Mandelbrot himself, and it wasn't because he created the set, it was more because he was able to visually represent the set using the IBM's beefy computers pretty much. But what's so impressive about this set is that no matter how far you zoom into the set, this layout right here will always reappear no matter how deep you zoom in. So if we were to go in to there, you'll see that each individual image right here at that layer is the same exact big layout of the Mandelbrot set. The big circle with the smaller circles coming off, and then the edges that look exactly the same. But if you were to zoom in any further than that, you would see. Next slide. If you zoom in even further than that, you would see that the basic layout is still the same, and this is zoomed in like 3 times, maybe 4 now. And you can see that the Mandelbrot set is still present and pretty relevant. So now we talked about fractals and the Mandelbrot set a little bit. But I'll hand it off to Juan to talk about what is important about a fractal.
So now we ask ourselves, why are fractals important? So fractals help us study and understand the important concepts, the important scientific concepts, such as the way of material growth. As you can see in this slide right here, this is the picture of a fractal. I was breaking down into material. This is basically how the material grows. And on the next, also we can study how scientists study the way of the frozen water. As we can see on this next slide, there's going to be a picture of frozen water. So here we can see that when the water is frozen down, we can see the snow, shows a snowflake. This is pretty popular nowadays during the winter time. And we got that from the frozen water of a fractal. Now I'm gonna tell you guys some facts about fractals, and well, on a daily basis we see fractals all around us, and we can see it in nature, as you can see in the plant, and how Linda was telling us about the kind of wave that he showed, that he explained. Also, we can see it in bridges, how bridges are created. Another fun fact that I found is that Ben Vandenbroek, he was a Polish mathematician, and he broke down the word fractals. He got it from the word from the Latin language fractus, which means broken down, which kind of makes sense how we broke down the bacteria and how it grows, and we can see the pattern. So now, Anna, can you tell us more about how he was organized?
Okay, so adding on to why it's important. So fractals came from the Latin word fractus, and this tree, I chose this picture because just like Duda said, how the branch is the main root of the fractal, it goes on into another branch, and each part matters. And can you go to my next one, please? It's a geometric pattern that we can simply see and use. And for the heart, I chose the heart as well in human body because fractals are all over in our human body, like in our arteries. And this one, like every valve matters, and it's just a repetition of different valves. And then the last picture, we can use it as a process to simply understand how we can create just the same patterns, just worldwide, or as big or small as you want. So, Luau, can I pass it on to you to tell us some more?
Yes, ma'am. Okay. All right, so I'll be covering the classification of fractals. Oh, shoot. So there are three kinds: exact self-similarity, quasi-self-similarity, and statistic self-similarity. Essentially, like in descending order, these are the levels of self-similarity in each of the fractals, or each of the fractals. Okay, so the first one is exact self-similarity. This is the strongest type of self-similarity of a fractal. So when zooming in on, when looking through different scales, one of the traits of exact self-similarity is that when you look at the fractal through different scales, it appears identical. As you can see with the Cook snowflake, it keeps repeating itself. And so so quasi self-similarity is nearly identical to exact self-similarity, except that when you zoom in, or like when you look at an image through a fractal through different scales, the fractal appears distorted or degenerated. The example I chose was the Mandelbrot set. As you can see, they're not exactly identical. It's sort of like looking at an exact self-similar fractal, but like on LSD. And the last one is the statistic self-similarity. This one is somewhat of a technicality. Most definitions of fractals include some clause about statistic or mathematical self-similarity. So the example I show, and they're generally random, sort of. If you're a statistical self-similarity, you will be. There's like some you were like generated randomly, generally. The example I chose is Brownian motion, which is the tendency for particles suspended in liquid to is the tendency of particles to move after colliding with another particle. So you can see that it's random, but it's like technically a fractal. So yeah, that's us.
Questions? All right. I can tell you that's probably one of the more entertaining ones that I've had in my 6 times of doing this. I'm sorry, 12 times. Very good. I liked it.